as you can see, this was our initial design and it was an absolute failure. So the part that didn't really work was the hill. It was supposed to be 20 centimeters according to the standards, and we just cannot make the marble go off the hill. This is due to the fact that our initial height wasn't high enough so that there isn't enough potential energy when it comes down to reach the hill due to friction. Now, we have tried lengthening the height so that it is higher, therefore more potential energy will be gained according to the calculations MGH, which is for potential energy. However, there is the issue that because the board, the space we're given work with is very short, when we give it more height, the initial hill, it will be too high and there will be a straight drop. Now, a straight drop will be very problematic because when it is straight drop, it goes straight onto the bottom of the tubing, and then, according to Newton's third law, each force has an equal but opposite reaction force. The ball will be pushed backwards by its own fall, therefore rendering it to achieve less velocity than it would have done with a less of a height without a straight drop. Therefore, there is no possible method for us to create a possible solution to make the marble go over the hill, so we scrapped this idea.
So this is the final design that we adopted. So we first have a hill that is 0.47 meters, which is 47 centimeters high. And then as we descend, there's a loop in between, which has the diameter of 15 centimeters, 0.15 meters. And as well as we have 270 degrees turn. So having this roller coaster design like this, it makes the calculation of the statistics much more easier than the design that we previously have. So first, we can calculate by using the centripetal force formulas, and we can get the velocity when we're at the first loop. And for the second 270 degrees turn, we can see that there's also a circle formed in here, and then the radius is shown. So it's much easier to calculate the acceleration and velocity of the roller coaster when you pass through the 270 degrees turn.
In our design, we apply elliptical loop rather than circular loop because we can see it that elliptical loop, it has a smaller radius compared to a circle. So which means that according to the this equation, B equals to S over T, like 2 pi r times zeta over 6c over t. The t is fixed, so as radius decreases, the velocity will decreases, and that is very important when we apply this to our conservation of energy formula, because the initial energy will equal to the final energy. And you can see like the potential initial energy, which is mgh, plus kinetic initial energy, which is 0 because there is no movement and no velocity, and that will equals to final potential energy, which is at the highest point, and that number is fixed, and plus 1 over 2 mass plus v squared. And mass is fixed in both sides of the formula. So as velocity decreases, the height will decreases, and the decreasing height will be very convenient for our design for the loop.
So we initially tried to build a device which is containing a pulley and a little stick at the top of the big hill, so that we can have a weight and a marble, and the weight will carry the marble up to the roller coaster, and then we will release it by pulling a stick, and the marble will fall down. And the weight is slightly bigger than the marble. However, as we tested this out, the weight and plus the marble, these two weights will cause this whole orbit to be pushed down. And since foam that we use is soft material instead of like plastic or metal, which is harder and will not shape will not get changed. So this is proven unsuccessful.